Okay, welcome back, guys. Today we're going to talk about how to evaluate a polynomial different ways, and we're going to graph some polynomials, and I'm going to show you how to maybe do some modeling in real life scenarios. So the first thing you do to evaluate a polynomial via direct substitution is you plug the x value in for x in the function. So notice I would get 5 parentheses 4 to the third plus 4 squared minus 4 times 4 plus 1. You could, on your calculator, type each of these in with parentheses. That is one way to do this, and then I'll show you how to do it by hand also. You want to make sure it's typed in correctly. So notice I'm getting, oh, mine cancel. So, but anyways, another way to think of this is just get 4 cubed, do the exponents first. So 4 cubed, 4 times 4, which is 64 times 5 out front. So that's 320. So you always do PEMDAS, right? So 4 squared is 16. Negative 4 times 4 is negative 16 plus 1. So we can add across. Notice these two cancel and you get 321. So what that means is when x is 4, y is 321. Now, if I type this in just like in my calculator, 5, let's see if I can get it right this time. You get the same answer. But you have to have the parentheses, okay? Another way to think of this is if you were to graph that polynomial in your graphing calculator, 5x cubed plus x squared minus 4x plus 1 and hit graph, you'll see a bunch of terms. It's a cubic, so you should have two terms on it. But what will happen is if you go to the table, 4 hits 321. So you can do direct substitution via technology also. So you can decide which way you like. But I always tell kids usually it means just plugging -2 in for x. So let's do another example. Notice the -2 goes in for the x in the parentheses, and then we can evaluate its output. So I like to use PEMDAS just to practice some of those mental math skills, right? So like when I look at this, I say, okay, I got -2 to the fifth first. You got to do that in parentheses. So that's -32 times 3 out front. That's -96. This next piece would be -2 to the fourth first. That's 16. Put the negative out front. It's at -16. Then you get -5 times -2, which is +10, plus the 10 at the end. So now I can just add across. I got -96 minus 16 plus 10 plus 10. So notice you get -92. So keep in mind you can follow the same strategy. You can type this into your graphing calculator as a function to get the visual behind this polynomial. So make sure it looks just like it and hit graph. So you get a small picture of the polynomial, but the table is going to be more important. So when x is -2, your output's -92. So direct substitution will work well. Another way to evaluate a polynomial is to use what's called synthetic substitution. So what you do with synthetic substitution is you take the given x value and you put it it out front of the polynomial, and you draw an upside down division bracket. Okay, so what happens is, as long as the polynomial is in what we call standard form, you take the numbers in front of the x terms and the constant, and you lay them out right here. 5, 1, -4, 1. And they have to be all in order. If you have a missing exponent, you have to put a 0 in this place. So you have to be careful. So what happens is you bring down the first term, and then you take 5 times 4 out front to get 20, which goes into the next column. Add 21 to get 21. 21 times 4 is 84. Add the next column, you get 8. 80 times 4 is 320. Add the next column, you get 321. That's your output. So we actually did the same problem as this one via what we call synthetic substitution. So I like this method the best. So we can try the same thing with the second scenario. The given x value, -2, draw your upside down bracket. 3, -1. Notice there's no cube term. 0x cubed and 0x squared. You got to put them in their places. Okay? Then the -5, and then the 10. So you always go from your highest exponent down to your lowest. First step, bring the 3 down. 3 times -2 is -6. Add the next column. -7 times -2 is 14. Add the next column. 14 times -2 is -28. Add the next column. -28 times -2 is going to be +56. Add the next column. 56 minus 5 is 51. 51 times -2 is -102. You add the last column to get -92. Same answers up here. So let's try one on our own. So if I was given a similar look, and let's pick in any number to evaluate this polynomial. So they don't give us one, but we're going to give you a value of x. So let's say we want to evaluate x when it is 2. Okay, so what you can do is use synthetic division, or we call it synthetic substitution here, where you take the value and plug it in. 2 is going to be evaluated synthetically by taking the coefficients of the polynomial. 5, -2, 10, -15. Carry down the 5. 5 times 2 is 10. Add the next column. 8 times 2 is 16. Add the next column. 26 times 2 is 52. And then you add the last column. Okay, so 52 minus 20 is 32 plus 5, 37 is your answer. So that's the output. So if I were to check this on my graphing calculator, 5x carrot 3 minus 2x squared plus 10x minus 15, and hit graph, you would see the output for that input by looking at its table. Second graph. 2 hits 37. That's your output. Pretty smooth enough. All right. When we graph a polynomial, we basically do what I showed you with the other examples. But I do want you guys to see a few features. Okay. Because this is an odd degree function, the leading coefficient that's a +1, we know it's going to have 2 terms, and it's going to go up as you go left or right across the graph. How far that goes up and down can be seen on your graphing technology. They call these points where they turn, this point right here is called a relative max, and this point is called a relative min. Okay, so the y-intercept is -1. I can tell the c-value is where it's going to cross the y-axis. So what we could do is we could use technology to graph this function. You could either use Desmos or a graphing calculator. Well, while I have a graphing calculator, let's type this in. X cubed plus 2x squares minus 1 and hit graph. So you can see how it has two terms on it. There's your max and mins, relative max and mins. The end behaviors go in opposite directions. And I can tell their table can be produced by second graph. So basically you're going to copy a few important points. One of those would be the y-intercept. So we know that when x is 0, y is -1. That's one of them. You can tell right there. Some other ones you may want to include are ones you can fit on the graph, like -2, -1, and -1, 0. That's an x-intercept, right? 1 hits 2, 2 hits 15. So the idea is, let's sketch this, and I'm not sure I like how low this got, but we can get a good sketch here. So -2, well, let's do this. Let's move this up, get rid of this. So go left 2, down 1, there's 1 point. -1, 0 is right here. 0 drop 1, 1 hits 2. 215 is way up here, right? So you know it's going to go through these two terms and come back up at 2 hitting 15. And then it's going to go down very fast. If you look at -3's output, it's way down at -10. So the idea is you want to get a good sketch of some of the turning points, where the relative max and relative mins are, and maybe some of the x-intercepts, if you can see those well. Now these aren't pretty intercepts, only one of them is pretty. So the idea is to get a good sketch, okay? Once we understanding what these look like, you're going to get better at recognizing them before you can graph them. So like this one is an odd degree function, and the end behavior is going opposite directions. That's important to see. If there was a negative out front, it would reverse the direction of the end behaviors, okay? Because it remember, it would reflect over the x-axis. So if I had one like this, there's a negative out front, so we know it opens downwards. The 4 degree means it should turn 3 times. It always turns one less than the degree, okay? The y-intercept is -3. So 0 down 3 is definitely where it hits the y-axis. So if I were to use technology, which is the quickest way to do these guys, we could check to see what it looks like. So -x caret 4 -3, and you hit graph. Notice it kind of looks like a parabola, and you actually can't really see the turns. It's probably very small. So it'll look more like a parabola. It's just a multiple of one. Okay. Second graph, you got your table. So I noticed, well, 0, -3 is at one of our important turning points. I noticed -1 hits -4. I noticed 1 hits -4. And then the other ones drop real fast. So basically, you're going to get a sketch that looks like this. Left one down 4, right one down 4, and it almost looks just like a parabola. Although there are some terms that are probably going on with it in here that we can't see because it's very small. But if you do a generic sketch, you'll see what the overall picture looks like. So in this case, we only can really see one main turn, and that's where the y-intercept's at. Okay, good. All right, so let's look at another application of this. So you might have situations where they start looking at polynomial functions. This one deals with the African wild dog. And The estimated population of the African wild dog under human care can be modeled by this equation, where T represents the number of years after the year 2000. So what we can do is use technology to graph what this thing looks like. It's an odd degree function, so we know it's going to have two terms on it typically. The y-intercept is 286. So let's use our technology to graph our function. Make sure you type in just like you see it and hit graph. Now, we cannot see the entire picture of this. So what's important to do, guys, is learn how to zoom out and in and kind of see what's going on, right? Because you want to see from year 1 to 18 and describe the behavior of the graph in this interval. So that's all the way from here to here. So what you got to do is separate. So basically, you look at your graph. You know you got the x-axis. You want to separate the window from 1 to 18. And then the y-axis, you definitely want to go up to 286 because that's your y-intercept. Okay. So one way to do this is to hit the window button, put your x-axis from, let's go from 1 to 18. Okay, you can go further than that too, but we're just gonna go year 1 to 18. Okay, and then the y value, you're gonna go from 0 all the way up to 286, and now hit graph. So we might want to go a little bit above 286 or below just to see because it's not showing up too well here. So I'm gonna hit the window button. See if they'll let me do this. Still thinking here. And let's try to adjust the settings to make sure we can see what's going on from years 1 to 18. So my calculator is cracking out. That's funny. Let's see if it'll let me reset. Okay, so here's our window. Let me go up to like 400. So the Y max is up to 400. Let's see what happens now. I still can't see anything. Okay. So sometimes Desmos is a little bit easier to change these windows. So sometimes I hit zoom and let's see here. No, that won't do it. It's been a while since I messed with these. Let's try that. Let's hit zoom and we'll zoom out. Still can't see it. So we gotta start. We just want to see this turn. That's the hard part. So it kind of gives you an idea. Okay, here's some points on there, but let's see if we can get this to pop up here. Hold on. Z standard is this one. So that's part of the graph. The window, I'm going to just change it from 0 to 18 for the x values. And for the y value, we're going to try to get it to pop up here. So we're going to go y min 0. And let's do y max up to, because it's definitely over the y-intercept of 286. So let's do 500. And then let's hit graph. So now I can start seeing it. So I might have to go a little higher. So I'm going to hit the zoom button and change, or the window button and change this to maybe like 1,000. So now I can see a little bit more. We want to make sure this equation is typed in exactly like it is. And where I messed up, I see it right here. No, we got minus 11.45x. I forgot my x squared. Look at that. One little change in the equation will mess it up. So we got to be careful. And this is a good learning moment. So I'll just make sure this is all typed in correctly. Okay. And then plus 286. Now if I hit graph, I can see everything. Look at that. So that's on me. So now I can see the zoomed in. I changed the window where the X's went from 0 to 18. The Y's went from anything, above that Y intercept. So I can kind of see it a little bit better. Okay. Now in Desmos, you might be able to see this a little bit better if you zoom in out and in. It's a little bit easier. Okay. So the moral of the story is now I can see everything that's going on. I have basically two turns going on, two changes in fluctuations. Okay. So what we would argue is describe the behavior. We would just say two changes in population fluctuations. So in other words, we got a relative max and a relative min going on. So it changes and goes back up down through the years. Okay. Now they might ask you some questions about this that will help you tremendously. So they'll say, okay, what's the average rate of change in the number of dogs from 2001 to 2018? What you could do is you could take the table and you could take the coordinates after the first year. One hits 384.42, and then year 18, if you look at your output, hits 696.38 or 693.38. And then what you could do that basically what's happening is if you look at the sketch of that graph, right, it's kind of going like this, it's going up like that, right? So one is here, and that's this output. Year 18 is over here, and you get this output. So when they talk about this average rate of change, that's a fancy way of saying what's the straight line slope between those 2 points. So really all you're doing is calculating the average straight line slope. So we use our slope formula. Y2 minus Y1, 384.42 minus 693.38, all divided by 18 minus 1. So let's go ahead and calculate that. 384.42 minus 693.38, all divided by 17. Okay, so actually, what I got to be careful here. When you set this up, if I did this is y2 and this is y1, this would be x2 and that's x1. So I got to flip flop these two. So I get 1 minus 18. I got to go in the same order. Okay, so notice to be over negative 17. So notice you get 18.2. So what this means is that the average rate of change per year is about 18.2 dogs per year. That's the increase. So let's make a note. You increase linearly at 18 dogs per year. So this is more of like a short-term estimate. Okay. Now, if you were going to say, do you think this model can be used after 2018? That's continuing afterward. If you look at your graph, guys, let's go ahead and notice, like, look at the table. It changes, but it's just more, not as consistent. So it goes up, keeps going up. So it's not as very consistent as what in the long term. So what I would argue is based on these models, more time it's more of a short term type model. Okay. So I would just argue because of the fluctuations going on, I would argue this is more better for short term. So you can say this is a better short term model. All right. So what you're going to end up doing is practicing these skills today. So I want you to add to yesterday's assignment. So this would be day 3. And I want you to go ahead and work on some of these. I will post some solutions for these to help you guys do well, okay? But in the meantime, remember you can also type these into Desmos. And sometimes it's easier to see all the changes if you zoom in and out in decimals between those years versus having to use a graphing calculator to change the window to see it. So either way, you can study the fluctuations in the models. All right, guys, have a great day. We'll see you tomorrow.